All right, let's talk about the chemical glue that literally holds our world together. I'm talking about everything from the water you drink to the very air you're breathing right now. It all comes down to something called the covalent bond. So, what is this invisible force, right? What's holding atoms together to make up, well, everything? It might sound complicated, but the answer really boils down to two simple ideas: sharing and stability. So here's how we're going to break it down. First, we'll look at this quest for stability. Then we'll see how sharing is the answer. We'll dive into whether atoms share one, two, or three pairs of electrons, tackle a question of fairness, and wrap it all up with why this bond matters. All right, first things first. To get why atoms even bother to form bonds, you've got to get inside their, well, not heads, but you get what I mean. You have to understand what they're trying to achieve. And really, it's all about one thing: stability. Think about the periodic table for a second. There's this one group over on the far right, the noble gases. They're the cool kids of the atomic world. They're totally unreactive, super stable, and just content. And pretty much every other atom out there is just trying to be like them, trying to get that same stable electron setup. And you know what the magic number is to get into that exclusive club? It's 8. This is something we call the octet rule. For most atoms, the absolute goal is to get 8 electrons in their outermost shell. That's the ticket to that noble gas-like stability. Now, like with any good rule, there's a big exception, and that's our friend hydrogen. It's so small it doesn't need 8 electrons. Nope, hydrogen is perfectly happy with just 2 to complete its outer shell. We call this the duplet rule. So the mission is clear: get a full outer shell. But how do they do it? And that leads us right to the heart of this whole thing. See, if an atom can't just give away or steal an electron to get stable, it has another trick up its sleeve. It can share. And that, my friends, is a covalent bond in a nutshell. It's a chemical connection, a bond, that's built on 2 atoms mutually sharing electrons. You see this happen most of the time between non-metal atoms, the ones that have a pretty similar pull on electrons. And here's the really clever part. When those 2 atoms share a pair of electrons, both of them get to count those electrons as part of their outer shell. It's like a perfect partnership. It's a total win-win that lets both atoms finally get the stability they've been searching for. Okay, but sharing isn't always so simple. It's not a one-size-fits-all deal. Depending on just how many electrons an atom needs to feel stable, it might share 1 pair, 2 pairs, or even 3 pairs of electrons. Let's take a look. So if they share just 1 pair of electrons, we call that a single bond. A perfect example is 2 hydrogen atoms coming together. If they share 2 pairs, you get a double bond, like the one that holds the oxygen molecules we breathe together. And if they go all in and share 3 pairs, well, that's a triple bond. Super strong. It's what keeps the nitrogen in our atmosphere so stable. And that's the limit, by the way. 3 is the max. A triple covalent bond, like that one in nitrogen, is the most sharing you'll see between 2 atoms. And because of that, it creates an incredibly strong, really stable connection. So now we've got the mechanics of sharing down, but let's ask a pretty important question. Is this sharing always fair? Is it always equal? The answer is a definite no. And this little bit of unfairness has massive consequences for, well, everything. This basically leads to 2 different situations. On one hand, you have what's called a non-polar bond. Think of this as a perfectly balanced tug-of-war. It usually happens between 2 identical atoms, and the electrons are shared perfectly equally. But then you have a polar bond. This happens between 2 different atoms, and it's an unequal tug-of-war. One atom pulls the electrons a little closer, creating a slightly negative end and a slightly positive end on the molecule. So what decides who wins that electron tug-of-war? It all comes down to a property called electronegativity. It's basically a measure of how strongly an atom can attract those shared electrons. The atom with the higher electronegativity is the bully on the playground. It pulls the electrons closer, and that's what causes that unequal sharing in polar bonds. Okay, so we've been deep in the weeds with stability, sharing, and fairness. But let's zoom out. Why do we even care about any of this in the real world? This is where we connect all these tiny little bonds to the stuff we can actually see and feel every day. Here's the most important thing to remember. Covalent bonds are the superglue inside a molecule, holding its atoms together super tightly. But the forces between separate molecules? Yeah, those are often way, way weaker. And that one simple idea explains so much. It's why things made of molecules, like water or even candle wax, have pretty low melting and boiling points compared to, say, a chunk of metal. It's fundamental to understanding why water's a liquid at room temperature and the air we're breathing is a gas. And that really leaves us with one final, fascinating thought. We've just talked all about how these strong covalent bonds create stable molecules. But what happens when you break them? If these bonds are the glue holding everything together, what happens when that glue comes undone? Well, the answer to that is the story of every single chemical reaction that powers our world.